So that was the walkthrough of the pseudocode. I know it might appear a bit fuzzy to you. Let's go over a concrete example. Right. So in the example, again, we have 6 routers and there are links. Each link comes with a cost. And let's assume U is the source and Dijkstra is going to do the computation starting from U. Now the initialization phase says let's include the source into the M prime. Therefore, we see U here appearing in M prime. Next thing is to go over all other nodes. Okay. So X, W, V, Y, Z. Those who are adjacent to U, then we set the minimum distance to it, set the predecessor to reach it. Okay. Otherwise, if they are not directly adjacent to U, set the distance to infinite. So for Y and Z, we'll see, okay, this should be infinite. And for VWX, V, the distance to V should be what? The link cost between the source and V. So between U, V, link cost 7. So 7 should appear here. The predecessor for such a pass definitely going to be A, because we just added A to the M prime set, right? And we're reaching V through a direct link. Therefore, the previous node must be the source, U. For W, link cost being 3, so 3 here, predecessor again U. For X, link cost being 5 and predecessor U. And yeah, 7U, 3U, 5U, infinite, infinite. Okay, so we just finished initialization phase of the Dijkstra algorithm on the example. Now, entering the looping phase. First thing we do in the looping phase is what? To find the I that is not yet in M prime such that the shortest distance to I is the minimum. And we add that I to M prime. Alright, so let's go over the DI. Okay. 7, 3, 5, infinite, infinite. Which one is the minimum? Yeah, 3 here is the minimum. Therefore, I is W this time, and we'll include I into the M prime set. That is why. Next, we see U and W both in the M prime set. And then we can now do the second thing we do in the loop. We'll update the minimum cost. And we're going to do this for all the nodes adjacent to, what is the I being added there? W, right? So we'll go over all the nodes adjacent to W. Okay, and that is now already in M prime. So who are the nodes adjacent to W? X, Y, V, Y disconnected, okay, because there's one link here, and U, all right. But you know what? U is already in the M prime set, so let's remove this. So there's just 3 nodes, okay, can potentially be J, and we need to update the minimum distance and the predecessor node. So what we'll be doing here is to exploit W here, okay, as a hopping node. So V here, okay, there's another pass, right? Originally, we had this direct link, but now there's an alternative pass through W, which is what? 3 plus 3, okay? The minimum distance to W plus the link cost between V and W. And that is how much? 6. Is 6 better than the existing minimum distance to W? Existing minimum distance to W, existing minimum distance to V is 7, and that is indeed better. Okay, so 6. And in case it's better, the new pass is better, we'll set the predecessor to the new node we are hopping through. So V is now taking W as the predecessor, and the cost, minimum cost from the source, is only 6. Second neighbor, Y. Previously, dy infinite. Currently, if we use W as a hopping node, 3 plus the link cost between W, Y, 8. Together, 11. Obviously better than infinite. And the predecessor is what? W. Third neighbor of W, X. Exploiting W as the platform, hopping, and then adding the link cost between X and W, that is 7. Is 7 better than dx? Dx was 5. 7, oh, yeah, in X's case, not better, so we'll keep 5 here. Z not being connected, it will remain the same, so remaining infinite. And therefore, we should see 6W here, 5U here, 11W here, and infinite here. So what do we do next? Well, we're in the loop, and we are not in the condition to end the loop yet, so we're not yet done. We have only U and W in M prime. Okay, there are more nodes. Okay, we could consider adding to the M prime set. And the way we add to the M prime set is to pick I such that di is the minimum. So dv6, dx5, dy11, dz infinity, which one is the minimum? Yeah, x is the one we're picking this time. So we'll include x into the M prime set. And we see there, x here is the I. So we'll be examining all the nodes adjacent to x next. So x is here. The adjacent nodes include u, w, y, and z. But you see, yeah, we'll be going over all the nodes adjacent to y, but not yet in M prime. U and w are already in M prime, so we will not be updating du, not updating dw. So let's update dy. The way to do it is to follow the formula. What is dy now? The current cost, 11. What is the newly discovered path cost? What is the new path? Well, one can actually go to x and then using x as a hopping platform to reach y. And the total cost is 5 plus 7. That is 12. This time, the new path is actually not better than the existing path. So we keep 11W here. The other neighbor, Z. Okay, what is the current cost? Infinite. So infinite here. Cost to x is 5. And the link cost from x to z, 9. So the new path discovered is 14. And the predecessor is x, which is better than infinite. So 14, x here. Now, v is not even a neighbor of x, so we'll just not update dv and pv at all. So, and that's why we see 6w here, 11w here, and 14x here. So this is the second iteration in the loop. And next, pick I again with the minimum di. 6, 11, 14. Therefore, we include this time v into the M prime set. Right? So 6 here included, v included to the M prime set. And therefore, the I is v. So I here. We'll go over all the adjacent nodes of v, which includes u, w, and y. And that's now already in M prime, so that includes u and w. The only node that we need to actually update the d for is y. So we'll be updating dy. Existing dy, 11, right here. So if v here is the hopping platform, the cost to go to v, the cost to go to v is actually what? 6, through w. The link cost from v to y is what? 4. So 6 plus 4, 10. Is 10 better than 11? Yes, it is. So let's update it. And this time the predecessor is what? V. Okay, so that is also saying this pass here was no longer good, and this is actually a shorter path. Now Z is not directly adjacent to V, so we just leave this entry down. That is why we see 10V and 11X. Good, so yet another loop. We pick another I with the minimum DI. 10, 14, therefore we pick Y next. And Y is included into the M prime set. So Y is our I this time. So Y here. Go through all the adjacent nodes that are not already in M prime. So X already in M prime, W already in M prime, V already in M prime. Well, only one that is not in M prime is Z. So let's try to update the distance to Z. And again, follow the formula. Existing distance to Z is 14, so 14 here. Using Y as a hopping platform, which says, yeah, the minimum distance is 10, and the predecessor is V, so it's this pass here. And we are adding the link cost from Y to Z, which is 2. 10 plus 2, 12. Oh wow, so this new pass here is better than the existing pass though. Let's update this to 12, and the predecessor is what? Y this time. And so we should see, 12 and Y here. And the last loop is to include the only remaining node, that is Y, actually that is Z here, okay, into the M prime set. And there are no neighbors adjacent to Z that's not yet in M prime. So this part we don't have to execute for the last iteration. Okay. And by now we've completed the Dijkstra's shortest path algorithm, okay, for an example of 6 nodes. Just a couple more notes to construct the shortest path to a particular destination from the source. Say from U to Z. Okay, what it needs to do is just to track the predecessor node, okay, and that's trace it all the way back to the source. So Z is the destination. That's traced back from the predecessor of Z, which is indicated here being Y. And who's the predecessor of Y? Yeah, it's stated here, which is V. Who's the predecessor of V? Stated here, W. Who's the predecessor of W? U. That is the source. Yeah, therefore you see, this is the shortest path from U to Z. The shortest path to X, yeah, indicated by the predecessor, which is U itself. And so we could actually reconstruct the shortest path by just tracing back the predecessors. Okay. And you see also here, if we trace back, okay, for all possible destinations to the source, you see also a tree rooted from the source U, okay, to all the destinations. And this is indicating also the shortest path to all the destinations. And such a tree is also called the shortest path tree. And Dijkstra algorithm there is also used to calculate, okay, to generate such a shortest path tree. Second note, the D values, okay, when we're picking the I, can have a tie. So in that case, we just have to break the tie and picking one of those.